Okay, so hello everyone. So first of all, let me thank the organizer for giving me this opportunity to present my work here. And here comes the title, Quantum Complexity in Rule-Based Constant Many-Body Models. And I will talk about scars, fragmentation, and quantum chaos. So this discussion will be based on this work that we did with one of my PhD students, Orko Prabhu. And here is the quick outline of the talk that I will more or less follow. So I will start the discussion with thermalization of post-quantum system. Then I will introduce the physical models that escape thermalization and we call the kinetically constant model. And I will tell why they are interested, why we are interested about those models, specifically for quantum technological applications. Then I will talk about two interesting properties that come from these kinetically constant models. So appearance of Hilbert space fragmentation and quantum scars. And then I will try to show you that how we can use quantum information theoretic measures to characterize those kinetically constant models. And then I will talk about the things that we are exploring along that direction currently. Okay, so the thermalization that I will be talking about is basically in the case of when we have a closed quantum system. And there we can define the notion of thermalization in the following way. So let us try consider an initial states evolution under some Hamiltonian. Now it happens that if we see the fate of a local observable, so the time dynamics of the expectation value of local observable, so if it happens that the long time behavior basically becomes close or equals to the thermal expectation value, then we'll call the system has been thermalized. Now in this regard, this eigenstate thermalizing hypothesis has been found to be very successful in describing that why it happens so. But there are of course notable exceptions. But in our case actually, so we will be first trying to see that the models which actually thermalize and which do not thermalize. So do we have the answer? So let's start with the this question that which system do not thermalize. So we have answer to that. So if you are considering integrable system or non-interacting system, so there we may have many conserved quantities, so they don't thermalize. But the question is that whether the opposite thing is also true. So if we just add interaction, so that will imply that the system will thermalize, or it is necessary as well as sufficient condition. So we have counter example to that. So for example, if we consider this model, so this X6Z model in presence of strong disorder in the magnetic field. So this is an interacting model, but in the limit of strong this disorder, so the system enters in this many-body localized phase, and in other words, the system do not thermalize. Okay. The next question that we are now asking is that, so are there any other system other than this disorder system, so which are or the clean system that thermalize or that prevents or escapes from thermalization? So here comes the model, so that actually does this thing, or that can that are clean system and that can escape thermalization, which are kinetically constant model. So let me very quickly introduce. So what do we mean by this kinetically constant model? So I will start with a very simple example. So let's say we are considering the evolution of a basis states under some Hamiltonian, and we know that it under the action of this Hamiltonian, so this basis state will evolve. If it is not an eigenstate, so it will evolve to other states. But how about if we enter in a situation where these basis states remain frozen, or there is no evolution of the states? Then we'll call that basically the basis states get. Those are the model which we call as the kinetic constant model. So one paradigmatic model is basically this PXP model. So there are experts here in this conference who has developed many interesting things along this direction. So where this P are the projectors, X is the spin flip operator or Pauli X operator. So if you act this Hamiltonian on this basis, then you will find that the basis which has two, let's say side by side excitation or two simultaneous excitation sitting sitting nearest to each other. So those bases are basically the frozen bases. So they don't take part in any dynamics in the Hilbert space. And this is not merely a theoretical model. So you can realize this in experimental platform. So using this something called this Rydberg blockade. So if you have Rydberg atom or an array of Rydberg atom, so then due to this presence of strong dipole-dipole interaction, actually you cannot excite these two nearest atom. Both of them you cannot excite. You cannot put in excited state. So this is in another way of saying that you cannot have this basis state in your Hilbert space configuration, or those are useless. Now, when in literature we talk about this kinetically constant model, so in last decade, so there have been two phenomena that actually people have tried to characterize for this model. One is the quantum many-body scarce states and appearance of Hilbert space fragmentation. So I will come to this one by one, but very quickly. So what do you mean by quantum scarce? So there are kind of atypical states, or those are very few number of states. Those are residing in the bulk of the spectrum. So let's say if you have a Hamiltonian, and if you are looking at the states, those are sitting in the middle. So those states behave very differently than the other states. Okay, so that's why we call them as an atypical states. And in what sense they are different? So they don't thermalize. Okay, so this is one notion, and often they can behave very peculiarly. Okay, so that I will show. But how to probe them? Okay, so how do you know that there are scarces in your model? So that's a very difficult job. So there are tools that you can exploit. For example, you can basically you can use some probe state like this Nell-like state, vacuum state, or periodic state, and you can basically see that there are some anomalous revival. Okay, this kind of thing can happen. Or when you take overlap with this probe state with the let's say the eigenstate of the model, then you will see that those overlaps for some certain state of states, those overlap could be very high. They may have very low entangled entropy. So those are the kind of, there is no rule book to find a scar, but those are quite widely explored tool that people use to find a scar. Now, these are also interested, we are also interested in this card because they actually can be served as in quantum memory. So there are recent works there where people are also using them in quantum sensing purpose, quantum communication. Okay, so those are the things that actually motivates you to look for, not only from thermalization direction, but from the other point of view, or that or where the thermalization is prevented. Now, the PXP model that I have showed you, so that actually exhibits this card, but it does not show this Hilbert space fragmentation physics that I am going to introduce. So what do you mean by this Hilbert space fragmentation? The idea is very simple. So when we let's say talk about the symmetry decomposition of a given model, so let's say you have a Hamiltonian and we are trying to let's say resolve the symmetry of the model. So then we know that the Hamiltonian can be separated or can be decomposed in many blocks which don't talk to each other. And due to presence of this kinetic constant, similar thing can happen in this KCMs or kinetic constant model. So you can find the Hilbert space may get fragmented in different dynamically disconnected parts. In other words, they don't talk to each other. So if you consider a state, let's say from one block and try to see its evolution, so it will remain confined in that block only. Okay, so it will not jump to other, so they are dynamically disconnected. So that's why we call there are dynamic. But remember that this fragmentation or this separation is not coming due to symmetry. This is coming only due to the presence of kinetic constants. So before I show our results, so let me fix two notions in this regard. So one is the strong Hilbert space fragmentation. So what do you mean by strong Hilbert space fragmentation? So let's say if I consider this small dl be the dimension of the largest scale of space, and capital DL is the dimension of my whole Hilbert space, then if this limit tends to 0 as I increase the system size, then I will call that this is strong Hilbert space fragmentation. In other words, the system will get fragmented in different, let's say small but many fragmented parts. And the opposite thing is that you can have a large but let's say a single fragmented part, so which we call as a weakly Hilbert space fragmentation. Okay, in that case, this small dl by capital DL tends to 1. So you have a single subspace which is almost occupying the whole Hilbert space. Okay, so now let's come back to the main thing, that the KCM that we are working with is basically not the PXP type that we have considered. So rather, so we consider in our work a family of kinetically constant models, so that can be mathematically represented like this. So I will explain all the term, let's say one by one. So if I just explain one of them, I think you can easily follow the action of the others. So let's start with this HN1. Okay, so for that, so I'll need let's say lattice structure. So this is a 1D lattice, and the action of this Hamiltonian, let's say this H1, so on a site I, quantum state that is defined on site. So that will be determined by the population of the, let's say, quantum states. Those are residing in nearest neighbor as well as next nearest neighbor. Okay, so that is the statement. So I will justify how this statement is coming. So how do you understand each term? So let's consider this H1. and try to split this, try to see this in a more elaborately. So this Ni, this italic or this curly Ni is basically, it's a sum of different projector terms. So the small Ni are the projector, so this 0 0 projector Nk, and this Nk bar are the projector, let's say 1 1 projector. Okay. So what this Ni operator does, sorry. Okay. So this Ni operator does this following thing. So if let's say we are looking at the evolution of the ith site, then the quantum state at site I will flip by this sigma ix operator, provided the sum of the population of its 4 adjacent sites equals to 1. So you have to sum up the population of its 4 adjacent sites. If it is 1, then H1 will act on this, otherwise it will annihilate that basis. So let me give you a quick example. This is the example. Let's say we are starting with 0 0 Si 0 1 basis state. Si can be 0 or 1. So you see the sum of the population is here 1. If I just sum this 2 0 is 0 and 0 1 is 1. So total population sums up to 1. So when I will act HIN on this, so it will change Si to Si bar. Okay. So this is the same way you can understand for the other HNK. In other words, I can write the action of this HNK is the quantum state at site I will flip, provided the sum of the population of its 4 adjacent sites equals K. So in this way, you get a family of KCM. Okay, just changing the simple rule, so you can basically get a family of KCM with different properties. So that is the simplicity of the model. So, but despite being simple, so I will show you that they can give you very interesting physics. So before that, let me also mention that some of the combinations of these KCMs can be also very interesting. For example, this HN2 plus HN3. So this is a very celebrated model called quantum game of life. So this is a quantum version of the classical cellular automata or classical game of life introduced by John Conway in 1970 to describe the evolution of living cell under some set of rules. Okay. So, and this classical game of life was defined on a 2D grid instead of 1D lattice that I am working with. So there they consider this 2D grid, and this EOL is a living cell, all other boxes are dead cell. So whether this living cell will survive or not, so that depends on a set of rules. Okay, so this is a very well-known model. And not only that, if you, and there's an interesting, let's say this website, so you can start with some initial configuration, and you will see that you will end up with many different, you can play with that. So if you keep it iterative, so after some, let's say iteration, you can see it can come with many complex structure. So there are also some other rule-based model in classical domain, so where different rules, so though they may appear they are very simple rule or very close by, but they can give you very different dynamics. Okay, so that's just a thing that this rule-based models are very popular in classical domain. Okay, so the first result that we characterize using this KCM is that so all of them are chaotic. Okay, so that's why despite they are having fragmentation, all these things that we will be discussing. So if we try to find out how this if you try to look at this this marker of quantum chaos. So one is this label spacing distribution, and another is spectral form factor. So then we have shown that for all this model, despite the rule, so they become chaotic. So not only that, so in terms of Hilbert space fragmentation, they show very rich physics. So they can behave very differently from each other, despite their rules relation are very close by. For example, if we start with this HN1, okay, so that shows very strong Hilbert space fragmentation. So here, this ratio, if you can see that from this plot, this ratio eventually goes to 0. In other words, it shows this strong Hilbert space fragmentation property. But if we just take the second thing, that if we just change K from 1 to 2, then we'll see that this is not a very good model to show Hilbert space fragmentation. So here it very basically shows weak Hilbert space fragmentation, and this ratio remains far from this thing. Sorry. Not only that, so if we consider this combination that I just showed you, this quantum game of life, so here there is no fragmentation at all. So some of these models, so theirs are close by, they can show Hilbert space fragmentation, may not, or strong, weak, many kind of possibilities you can explore. just by changing this rule. So here is just a summary of the things that you can come up with. This HN0, they have universal fragmentation, but trivial. Strongest comes when you are considering HN1, then H2 is weak, and you can then take other combinations. Now, why this HSF is interesting in our community? So you see, as I mentioned, the thermalization may be fundamentally interesting, but opposite of thermalization is also could be interesting if you are thinking about quantum memory. So slow down of thermalization, so those kind of thing can actually help you to preserve the coherence, okay, or apply those system in quantum technology or other related areas. Now, so now remember, as I mentioned, that in the symmetry case also, so you can have this kind of block division of your Hamiltonian, but those blocks can be characterized by some good quantum numbers, right? But for the Hilbert fragmentation, we don't have such, let's say, such identifier that you will characterize this fragmented subspace by some good quantum number or so. So that's why we try to see that how about if we use some quantum information theoretic measure and try to see that whether we can characterize them using those. In other words, when we are exploring those, let's say, fragmented subspace, so how much they are complex in terms of, let's say, quantum state preparation complexity, okay. So that can be quantified using two measures, in our case, entanglement and non-stabilizerness, okay. So I'm not going to define them here, but if you are interested, I can talk after the this presentation. So now here are the results, one that we got for the entanglement from the entanglement study. So if you, let's say, again consider this HN1 and HN2 and try to see the distribution of entanglement across the whole spectrum, then you will see there are some subarch like behavior, okay, and those are nothing but the behavior that is coming from, yeah, I will finish. So that are nothing but coming from this different fragmented sector. So this arch, so different arch correspond to different fragmented sector. But here comes an interesting thing. So common intuition may be that the largest fragmented sector or largest Hilbert space with highest dimension may give you highest entangled entropy. So that is not the case, okay. But in the static case, that is not the case. But when we try to see the dynamics, that means if we start from initial state and try to see that how this initial state is getting entangled over time, so then there is a relation between the size of the Hilbert space and the amount of entanglement that it attains in long time. So in the quantum game of life, so we see the arch becomes even more prominent. So this is more close to like thermal behavior. So we have already shown that this model has no fragmentation. So this behavior is also quite expected. So this shows very clean picture. So this I'm skipping for the non-stabilizer thing. So if you're interested, I can talk about later. Okay. But the last part that I want to show, so that is not the main thing, but still I would like to mention here. So which is basically the quantum scar. Okay. So the thing is that, so here what we have observed that this model has strong fragmentation on all variety of fragmentation property, but in terms of scar, they did not give us very hopeful result. Okay. So the only thing that we have shown that this HN0, so that is an unconstant PPXP model. So there are PPXP model already there in literature, and there you can find scar. So what we have shown is that if we part up those on this models, unconstant PPXP model with this defined kind of KCMs that we are considering, so there is a parameter range up to which this scar still survives. Okay. And why we are interested in studying this thing, okay, or this particular combinations? Because if we consider this combinations, so this HN0 by and delta HN1 or delta HN2, so this is let's say two KCMs that we found that host both scars and fragmentation. Okay, usually you may not have these two properties together, so that's why this is a very important or very particular choice of these KCMs that shows scar as well as this fragmentation. Okay. So yeah, so this is the thing that I want to mention. And about the possible experimental relation, okay, so this is I cannot give you an immediate answer to that, but we are now trying. So there could be like this, I mean, the possible direction could be this again, using this Rydberg platform, or maybe some flow key engineering, so where you can actually tune different interaction and implement those extra constant. But here, this is the thing that we are currently exploring, so that whether we can come up with a quantum circuit that will mimic the evolution of the KCM that we are considering in our work. So that is still undergoing. So just some repetition of the main thing that I have so far talked about. So here we have presented a set or a family of KCM. So that is, you can say, a little bit different than the already existing this PPX or PPXP or this family. So here the evolution rather, instead of this Rydberg blockade, so here the evolution is governed by simple rules, and there are models where you can find in classical domain there are analog models. And what we have shown that, so they can, even though they are structurally very similar, only separated by certain rule condition, but they can come up with different Hilbert space, different properties in terms of Hilbert space fragmentation or existence or absence of quantum many-body scars. So there are models where both of them can coexist. You can find that the pattern model that I have shown. Now, in addition to that, we have tried to characterize those different fragmented or the scale of subspace in terms of their resource generation capacity or in terms of their state preparation complexity. And again, so this is one thing I have mentioned, that we are trying to come up with circuit model. So two immediate things that can come up from here is basically open quantum system generation, and also if you consider, let's say, this normalization limit from this open quantum system paradigm. Okay, thank you so much. So this is my institute. So this year we are celebrating 100 year. So if you are around, I think you can please visit our institute. We will be happy to host you. So thank you so much for your attention.
Questions?
So thanks for the talk. One question I had is that in terms of, like, we were comparing entanglement and non-stabilizerness both in this. So like, I get why entanglement is a measure of chaos, but same thing, how can it be said for non-stabilizerness, which is just a measure for like calculating the non-Clifford cost of the circuit? And particularly in this case, like the Hamiltonian we are considering is ultimately just flipping the spins.
Yes.
So in that case, the non-Clifford cost should be less for each of the gates. So like in that, so my question is, how does non-stabilizerness is a good metric to classify this fragmentation?
No, we are not relating entanglement with chaos or non-stabilization with chaos. So there's a different notion of complexity. Okay, so this complexity is more at state preparation complexity. So how, let's say, if I want to prepare a quantum state, so let's say if it has high entanglement or high non-stabilizerness, so I'm trying to quantify this complexity using that. So, and then chaos comes as dynamical complexity. Okay, so you can have a, let's say, a chaotic situation where non-stabilizer can be low as well. Okay, so these are two different things. Okay, so that's why we call it a space, particularly that is a state preparation complexity. So how easily you can prepare a quantum state.
Yeah.
Thanks for. I have just a question that when we generally study the PXP model,
Right.
so we work on a projected subspace where there is no two workspaces.
Right.
So on. So in this case, when you are talking about this N0 or N1,
Yes.
where you're looking at 5 sites and searching for a flip,
Right.
where you have the total occupancy to be 1 or so. Are you working on a projected subspace or the?
No, this is, I cannot write as a single projector. So you see that if I break down this Ni, so these are the summation of different asymmetric as well as symmetric projectors. So I cannot just, I mean, project in a single like PXP kind of thing. Okay, so this Ni are the simple, let's say I have Ni bar, Ni, some of them. So that's, you can say it's a little bit relaxed condition than the PXP or PPXP this family has.
Okay, I see. And the second question I have that for the static field, you have this some of the eigenstates, they are the mid spectrum state has the anomalous large overlap with the late configuration.
What configuration?
The late
Yeah. The scar state, exactly you're talking about. Yes.
Here we have some.
No, that is the thing I mentioned, that this H0 is basically unconstant PPXPP. Okay, so there they have scars, and not all the other model. If I consider, at least using the standard tool, we could not find scar. But let's say if we part up this, so that's why I showed this model. So this is basically, let me show you here. Yeah, so there's a no scar for any HK apart from H0. H0 is PPX, PP in hidden, right? So, but if I, let's say, part of them, so sometimes they could just wash away. Okay, so there are cases where part of scar can be very sensitive. But what we have shown is that, so if I part up using this HN1 and HN2, so then there is still some region where you can still preserve the scar. And these models are also showing fragmentation. This is an example of model showing both. Okay, but for other HN, there is no scar. At least the diagnosis we have used, we could not find any scar. Okay.
Any other questions? I had a question. So, going back to trying to realize some of these in real systems, there are two ways we can think of getting constraint models or some effective models. One is we have extra Hamiltonian terms which are very large.
Right.
And so, you do some course training and
Right.
they run away and then you get some constraints
Yes.
where you are. And the other is, of course, you can just add some much smaller terms and then over some very long term, maybe in that time, maybe they'll take you out of this space. Do these two things have different impact when you, so instead of perturbing with a small term, suppose they perturb with a very large term, let's say like a Hubbard U term,
Okay.
where we get a no level occupancy space, but the actual model has higher energy states and then their term. Do you think the answers would look different, or do you have any sense of this?
Yeah, so in our case, actually, the part of Hamilton we also wanted to keep as a family of KCM. It's not just in Hubbard model, so that the part of model is also in KCM. And
I'm saying, suppose I add a very large perturbation,
right,
then in dynamics, I can integrate over some very fast timescales and get my effective
absolutely.
KCM. But when you look for things like entanglement, stabilizer, will they change?
That may change. That may change. That may change. But another thing I'd want to add that this KCMs, you can also, as you mentioned, that you can also come up with, let's say, small or large perturbation theory. So recently there have been proposal where you can actually come up with the same kinetically constant model from open quantum system dynamics. So you can generalize, you can have this dissipator that will give you this effective dynamics like this KCM. Okay, so this is another route. Okay.